So today we have the last lecture of the series. It will deal with quantization of the electromagnetic field. But before I go to this problem of quantization, I would like to mention something that will be the proof that complexification of electromagnetic field can be very easily used in a rather peculiar way. Namely, we argued that given any solution of the wave equation, of the D'Alembert equation, we can then easily, by differentiation, produce solutions of Maxwell equations, extending the method introduced by Whittaker. I want to show now some perhaps even trivial but quite interesting applications of this idea. And this rests on the following observation. If we have a function, some function f, say, of r and t, which is a solution of the D'Alembert equation, we can shift the variables and they will still be solutions of the equation. You may say that this is just trivial because that just means that we change the origin of the coordinate system. This is quite true. However, we can also do the following shift, namely from f of rt, we may introduce, for example, x, y, z plus ia and t. Or we may shift in the t variable using a complex unit I in the shift. This is definitely not a change of the origin of the coordinate system because we moved in the imaginary direction, so to speak. However, such a shift also does not change the solutions of wave equation. Let's take the simplest possible solution that is known to everybody, namely 1 over r. It is not the solution of the free equation. It has the singularity at the origin. This is the potential of a single charge, if we multiply it by E if you want. And everywhere else, except at this point, this is a solution of the wave equation, almost a trivial one, does not depend on time, but as far as the space derivatives are concerned, this is almost equal to 0, except at the origin where it produces 4 pi times the delta function of r. However, now applying this trick, we obtain something which is quite interesting. So we have 1 over the square root of x squared plus y squared plus z plus ia squared. This is a complex function, but we are not afraid of complex functions.
But also multi-value.
It has, yes, that's true. And this very simple trick, and I leave this to you as an exercise, has some very interesting electromagnetic structure. Well, first, when we are far from the origin, that is when z is much bigger than a, this is the Coulomb field, so we have a charge inside. However, when we come closer, this function becomes complex, and the imaginary part is the magnetic field. So the exercise for you is to study this potential using the trick, and from this potential we can produce the vector F. It will not depend on T, but it will still depend on R. And the question is, what is exactly the structure of the electric and magnetic field in this case? It's highly non-trivial, as you will find. And to give you a hint, you will find that the magnetic field is that of a magnetic dipole. So we have a magnet and a charge, and all that is obtained by such a simple shift in the imaginary direction. Another example of this category is a shift in the time direction for a solution of D'Alembert equation, and it also produces an interesting combination of electric and magnetic fields. Okay, that much as a postscript for the last lecture, and now we come to quantization. So, as I will try to convince you, the quantization is extremely simple in this language. And the simplicity will be seen when we compare what we get for electromagnetism with something well known, that is one-dimensional harmonic oscillator. Everybody knows what is one-dimensional harmonic oscillator. The energy of the harmonic oscillator in one dimension is p squared over 2m. The kinetic energy plus m omega squared divided by 2x squared. This is the classical Hamiltonian, and quantization proceeds along the standard ways. We replace x and p by operators, they commute to IH, and everything can be done algebraically. One doesn't have to solve the Schrödinger equation. One can do this by algebraic manipulations. How is that done? Let's stick first to the classical t and x. We may replace the variables p and x by complex combinations. Alpha is 1 over square root of 2, and here we have x, but we want alpha to be dimensionless, therefore we divide by some unit length, plus I, and here we, for convenience, introduce the same L divided by H and P. This is a classical complex function. Its complex conjugate is 1 over the square root of 2x divided by L minus I, LP divided by H. And from this we argue quite simply that alpha star alpha, that is the modulus squared of this. When we take the square, the cross terms cancel, and we have here 1/2 x squared divided by L plus L squared p squared divided by H bar squared. Well, this looks almost like our Hamiltonian. It has x squared and p squared terms. And we can indeed write the following relation, that H is equal, now this is dimensionless, x divided by length squared, and L squared p squared by H bar. Again, it's a dimensionless combination, so H, which has the dimension of energy, will be some gamma, factor of gamma, times alpha star alpha. And by comparing this formula with this expression, we can easily find that gamma must be equal to h omega, so we have the formula h bar omega. I will explain in a moment where does h go, and this is the same h as here, h omega, alpha star, alpha. So these are algebraic calculations. If we want to repeat now the same procedure for quantum operators, then we have the quantum Hamiltonian, which is built from operators p squared over 2m plus m omega squared by 2x squared. And there is a slight problem, which is well known. It has interesting physical consequences. Namely, if we replace alpha and alpha star here in the quantum case by operators, then we cannot drop the cross term, because the cross term of operators which do not commute will not, the two terms will not cancel, but they will produce the commutator, and the commutator is h bar, so one may show that this here, when expressed in terms of, so let me write this down not to confuse you, alpha becomes the operator A, alpha star becomes the operator A dagger. Commutation relations give us A operator A dagger operator equal to 1. Now, and this cross term, which will appear, leads to the following formula. In the quantum case, H operator equals H bar omega, and here we have A dagger. I will drop now the hats. These are operators, of course, plus 1/2. 1/2 comes from the cross terms. And this is well known. If you solve the Schrödinger equation, the result is the same. There is so-called additional zero-point energy. Now, zero-point energy is a physical fact which we cannot easily get rid of, and it leads to interesting consequences, as I will mention in a moment when I translate this into the electrodynamic case. For the single harmonic oscillator, 1/2 does not really count, because we can start counting the energy from this 1/2 h omega point, and then we have equally spaced levels for the harmonic oscillator. Now we come to the quantum electrodynamic case. How do we translate this now from single harmonic oscillator to the full electromagnetic field? Well, we have to remember what Planck told us. Planck said that energy in electromagnetic field comes in portions. When there is a change in energy, this can only occur in the form of quantized portions. And these portions are quantized in such a way that the energy of each portion is h bar omega. And in the language that Planck did not use, but it came later, we say that the energy of the photon, which has the wave vector k, is equal to h omega, where omega is equal to c times the modulus of K. So now we go back to what I told you before. We know the energy of the electromagnetic field because this is a well-known fact from classical electromagnetism. So we can write the energy, which means that we know the Hamiltonian, or the classical case, and the Hamiltonian is obtained by 1/2 of d squared plus b squared with appropriate factors to match the dimensions, and we obtain the following formula. d3k f star lambda summation of lambda of k f lambda of k. Where does this formula come from? It does come from the expression for the energy known from electromagnetism, d3r, and here is d squared divided by 2 epsilon plus b squared divided by 2 mu. When we introduce, instead of d and b, the complex combinations, the Riemann-Zilberstein vector, this simply becomes d3 rf star r f of r. Of course, maybe a function of t, however, the energy is a constant of motion in free electromagnetic case. And now we know the expansion of f because we know how to Fourier transform f. And if we use this formula for f, which is here the integral of d3k, the Fourier representation, 2 pi to the power of 3/2. Now we have the polarization vector, E of k, and multiplied by these two amplitudes, f plus of k, e to the minus I omega t plus ik r plus f minus of k. And as I said, it is convenient to call this the complex conjugate, even though classically that does not seem to be relevant, minus I kr. This expansion comes from the equations of motion, the Maxwell equations, by solving these equations in Fourier space, by Fourier analysis. So now all is said, and we can now use this analogy and try to quantize. Well, this formula suggests that we have full analogy, perhaps with some coefficient to match the dimensions, and we'll find the coefficients right now, some coefficients, and instead of one single amplitude in the one-dimensional harmonic oscillator, we have a function, one amplitude for each photon and for each polarization, either plus or minus. So now let's see what to do in order to have this full correspondence. Well, the expression at the top does not look yet like the energy because we are missing h omega. So what we will do, we will write this energy over the Hamiltonian in the following way. Now we say, I first proceed classically, so I don't put a hat here. We have d3k, and we divide by k, and I will explain this in a moment. I mentioned this division already before, but now it will be worth repeating. And here, instead of have the counterpart of this formula here, or this formula here, I write h omega, and instead of f, I write some alpha lambda and the summation of lambda of k star times alpha of lambda of k. By comparing this formula with this one up there, we see that I have just identified f lambda of k with the square root of hc times alpha lambda of k, where alpha is just proportional to f. It's a classical amplitude of the type that is needed to expand the field into Fourier components. So this is just the factor, which is the same as we had gamma before for the classical one-dimensional harmonic oscillator. In order to have dimensions right, we need something which has the dimension. But moreover, we want this to be exactly h omega in order to justify what Planck said, that electromagnetic field is quantized in portions of h omega. We may even go one step further here and write also P. P, I remind you, was built from the Poynting vector, is the momentum of the electromagnetic field, and if you do the same trick here, you find that this is h bar k times alpha lambda star of k alpha lambda of k. Now we quantize. Quantization means replacing the numbers, the functions alpha, by operators. And the rule for this replacement must be such that this is indeed the Hamiltonian, that is, it generates the time evolution of the system. And we know what is the time evolution of f just by looking at this formula. As time changes, f is multiplied by e to the minus I omega t. So the time evolution is quite trivial. It's just a phase factor. Maybe not trivial, but quite simple. And it's minus I omega t. And this must follow from the operators that we introduced, replacing these classical amplitudes. And again, we encounter the same problem as before, namely by replacing A star and A by operators, we should wonder what is the ordering in order to have something that will correspond to this 1/2. And here there's a problem, and this problem is a physical problem indeed. The question is that we want now to satisfy the following assumption. The ground state of the electromagnetic field should have zero energy, because if there are no photons in it, then the energy should be zero, which would mean that we just drop this additional factor, which is just a number. So it should not really complicate or spoil our transition from classical, because we just disregard the number by assuming that the ground state of the electromagnetic field has zero energy. Which means that we order creation and annihilation operators in the same order as they stand here, that is A dagger times A, and then the ground state will have zero energy. However, this turns out to be an important physical problem if we consider two situations. If we consider the electromagnetic field, which is enclosed with some boundary conditions. Like, for example, we have a cavity, and there are electromagnetic excitations inside the cavity. Then we have to impose the boundary conditions at the end of the cavity. If this is a metallic end, then we have to impose the conditions known from electromagnetic classical theory, that the electric field parallel to the boundary must be zero, and this is the proper condition for the metallic boundary, etc., etc. And now we have a problem of the following type, namely, we can compare two situations, say, cavity of a given length with a cavity of a bigger length. And the question now is the physical one. What is the energy difference between these two situations? And this is a source of phenomena known under the name of the Casimir Effect. And the Casimir Effect, roughly speaking, is an observation that even though if we have one single case, we can, by fiat, declare that the energy of the lowest state is zero, but when we have different situations, we cannot have the same for both. And even though if we put 1/2 here into this formula, we will get a nonsense, because an infinite number of 1/2 is infinity. When we compare two situations and take the difference in energies, then we find what is called the Casimir effect. And for example, this effect will tell you that when you have two cavities of different length, then the energy difference will depend on the length. And if the energy depends on the length, that means that we have a force, because the force is the derivative of the energy with respect to the length, and this is known as the Casimir force. So the problem of 1/2 is not an academic one. This leads to interesting physical phenomena. And that was just a side remark, and now we proceed further. So what we accomplished now by this analogy with one-dimensional harmonic oscillator is that we found the formula for the Hamiltonian, the operator Hamiltonian, which in the free case is h omega sum over lambda a dagger lambda of k, a lambda of k. These are operators. And what are the commutation relations? The commutation relations must be such that the time evolution is given by the commutator. And you may check that this is okay, except for this normalization. I can easily get rid of this k here just by saying that my new operators contain the square root that cancels this. Why I'm not doing this? because, as I mentioned before already, this combination is invariant under Lorentz transformations. Therefore, if this is invariant under the Lorentz transformations, and H is the fourth component of a vector, the remaining part of this vector is the momentum, for which I have written here the classical expression. Now we translate this into quantum expression, lambda, A dagger lambda of K, A lambda of K. And this is invariant, does not change under Lorentz transformations, but this object here forms a vector, four-dimensional vector, H bar, and then omega and K. And omega and K form a vector in four-dimensional space, which gives the proper transformation properties for H and P. What does that mean for A dagger and A? That means that under the rotations and under the Lorentz transformations, A dagger A do not change, because we already have a vector, and this should be a vector. This does not change, so this cannot change. And that means that this normalization, which is not loved by people working in quantum optics, is more fundamental, I would say, because that means that under all these transformations, creation annihilation operators can only pick up some phase, but they cannot change their normalization. And that means that we have to adjust the commutation relations accordingly. Here in one-dimensional harmonic oscillator, the commutator is 1. Since here we have a function of k for A, that means that this cannot be 1, but this, by analogy, would have the following form, by analogy with the classical case. K prime. Now 1 in for functions of K means that we have unit three-dimensional delta function. However, this is something, as I said, what quantum opticians would like. But if we want to keep this invariant normalization, then in order to have everything correct, we must introduce here a factor of K. And now we may check the dimensions and see whether everything is okay. H omega has the dimension of energy. Hamiltonian has the dimension of energy. Therefore, the rest must be dimensionless. D3k over k has the dimension of k squared. From this formula here, we see, since delta function has the dimension of the inverse of the argument, and there are three is delta functions, so the dimension of the delta function is 1 over k cubed, times k, we have 1 over k squared, and here we have k squared in the numerator. Therefore, the dimension of our Hamiltonian, as was to be expected, is the energy, and everything is okay. But as I said, this particular normalization, this is, you may say, just a technical problem, how we normalize these operators. This is something I prefer because of its connection with special theory of relativity. So by using this simple analogy, we quantize the electromagnetic field, so we can go back to our formula for the Riemann-Zilberstein vector and replace this by the Riemann-Zilberstein operator just by replacing these amplitudes by what I did in the classical case. We will have d3k to pi 3/2. Now we have this formula here from the f function to the operators. We introduce the factor of h bar c. We can write it even before the whole integral. And here we have e of k. And now the operator a plus of k, the annihilation operator, e to the I omega t plus I kr plus the creation operator for the left-handed singular circular polarization, I omega t minus I kr. Here it is. We quantize the electromagnetic field. If you want to compare this with some formulas you find in textbooks, you have to split this into the real part and the imaginary part, or in the case of operators, one should rather say into Hermitian and anti-Hermitian parts, and then you get more terms, because when you split, that means you add or subtract f with its Hermitian conjugate, and instead of 2 terms, you get 4 terms. But of course, this is what introduces the electric and magnetic field. Now, the question is, what is really the relation of this quantized description with the electromagnetic fields that we learn in the classical course of electricity and magnetism? Now, the first guess would be perhaps classical field is some kind of an average expectation value of the quantum operator. This one would expect from the classical limit of quantum theory. So let's take this operator f, and let's take some expectation value of this operator now in some state of sign. The first observation is rather disappointing, because if you say, well, let's believe that the classical theory is obtained when the number of photons is very big, then we go from quantum description to the classical, we find a problem. Because if we say, well, there are n photons here, very big number of photons, and we take the expectation value in a state of many photons, we get 0. Why do we get 0? Because f either adds a photon or adds or subtracts a photon. So instead of n photons, after acting with f, we obtain either n minus 1 or n plus 1. And of course, the state with n plus 1 or n minus 1 photons is orthogonal to the state with n photons. That's it. How come this happened? Well, this must be so because of the uncertainty principle. What is the uncertainty principle translated into the language of photons? The uncertainty is between the number of photons and the phase of the electromagnetic field. One may find that the commutator between the number, what is the number operator, say dagger A, and the phase is the conjugate variable, and there is a certain relation. If the number is fixed, the phase must be spread around, and the average is 0. So what is really the connection between the electromagnetic field described by Jackson or whatever and the operator F? What is the proper counterpart of the classical field described in quantum language? Well, this is the so-called coherent state. And we can learn what is the significance of a coherent state even studying the one-dimensional harmonic oscillator. The counterpart of the electric and magnetic field operators are X and P operators, as is seen from this analogy. And of course, if you take harmonic oscillator in a state with n excitations, then you get 0 for this by the same argument. And X either increases or decreases the number n, and this gives 0. So what is the classical state, or the closest possible classical state of the harmonic oscillator? It is the coherent state, which is built not from one n-photon state, but from many photon states distributed according to the Poisson statistics. Well, the first observation is the following. If instead of n, we take the sum n plus 1, this is linear combination of the nth excitation and n plus the first excitation. And then we evaluate this average in such a state, then we will have a non-zero value, because when x increases the value n, there will be a corresponding term on the left-hand side. The result will not be 0. As I said, the coherent state is a much smarter state because it is an infinite sum. I'll write it down just for a single harmonic oscillator, and the extension to the electromagnetic field is quite obvious. A coherent state, which is sometimes denoted by alpha, and this is more or less a related alpha to this one here, is given by some normalization factor, and here is E to the power of alpha times the creation operator acting on the ground state. What does this mean? This means that we add, if we expand the exponential into the infinite sum, we will have first 1, then the first power of a dagger, then 2 powers to the power of 2, etc., etc. So we have a combination here of the ground state plus 1 excitation plus 2 excitations, etc., etc. And this is indeed then something that will produce a non-zero value. Why this particular combination deserves the name of the classical counterpart? Because one may check that the average value of operator A, alpha, or a dagger is equal, I'm not neglecting the proportionality constant, is equal to alpha. So this state indeed makes the operator, average value of the operator equal to this complex number. And the same can be now translated, even though there are technical complications, into the full quantum electrodynamics. Of course, now the coherent state is built from many different creation operators with different values of k. So a coherent state will have some function, say g of k, which will characterize each particular value of the wave vector, and it may be different for different wave vectors. Now it is a relatively simple exercise using the commutation relations that will show you that the average value in such a state, which that we call G of F, of the F operator, it will give you the same formula as above, except that A dagger and A will be replaced by this classical function G. So we have a certain electromagnetic field described classically with a formula that will give you exactly the shape of this, and the shape of this is the same as in the one-dimensional case, except that we have different possibilities for different values of the k vector. Coherent states produced by lasers are exactly of this type. Laser does not produce an n-photon state, it produces a combination. Why is that so? Because the lasing process does not allow you to control how many photons were produced. You excite many, say, rubidium atoms, and then each of these atoms will radiate, but you do not tell the atom which atoms are supposed to give you the photon. Therefore, the number of photons is ill-defined, but we gain the phase is fixed, the phase is well-defined, and that is why the name coherent radiation is well-deserved. In a single emission process of an atom, the state is just a one-photon state, and of course the average value for a single atom of the field is 0. Well, I think this is the end, and I hope I will hear some questions now that may be the questions to any part in this whole series of 4 lectures.
Thank you very much.